West Antarctica is losing ice today, but scientists have now reconstructed a much older transformation that moved in the opposite direction. Around 3.2 million years ago, the West Antarctic Ice Sheet appears to have crossed a climate threshold and expanded rapidly toward a much larger, more stable configuration. The evidence was not found inside the ice itself. It was discovered in mud buried beneath the Amundsen Sea, close to the glaciers that are now among the most vulnerable on Earth. Researchers examined a continuous sediment record extending back more than 4 million years. Inside those layers, they found changing concentrations and grain sizes of magnetic minerals. Those tiny particles reveal when glaciers advanced across West Antarctica, eroded different types of bedrock, and carried the debris toward the ocean. The record suggests that West Antarctica once contained much less ice than it does today. Then the planet cooled, ocean temperatures declined, and the ice sheet gradually expanded. At approximately 3.2 million years ago, the pattern changed sharply. Sediment linked to the Thwaites Glacier region increased and remained elevated, indicating a sustained advance of the ice sheet. The central mystery is not simply why Antarctica gained ice. The larger question is why a gradual change in climate produced what appears to have been a sudden transformation in the behavior of an entire ice sheet. West Antarctica is fundamentally different from a simple block of ice resting on high land. Much of its bedrock lies below sea level. If the ice were removed, large parts of the region would become a deep archipelago separated by marine basins. That geometry makes the ice unusually sensitive to the ocean. Glaciers flow from the interior toward the coast. When they reach the sea, they often extend outward as floating ice shelves. These shelves do not directly raise sea level when they melt because they already float, but they act like braces that slow the grounded ice behind them. Warm ocean water can enter cavities beneath the shelves and melt them from below. If the shelves thin, the glaciers accelerate. The boundary where ice lifts from the bed and begins floating can retreat inland into deeper basins, potentially making further retreat easier. This is why scientists closely watch the Amundsen Sea sector, including Pine Island and Thwaites glaciers. Research has documented rapid modern thinning and grounding line retreat in this region, making it one of the most important areas for understanding future sea level rise. But satellite observations cover only a tiny fraction of the ice sheet's history. They reveal what is happening now, not how West Antarctica responded when climate conditions remained warmer or colder for hundreds of thousands of years. To look further back, scientists drilled into sediments on the continental rise beyond the Amundsen Sea. The layers accumulated slowly as particles sank through the ocean or arrived through underwater flows carrying material eroded from Antarctica. Every layer preserved a mixture of minerals from a particular period. By identifying where those minerals originated, researchers could estimate which parts of West Antarctica were being eroded by moving ice. One of the most useful minerals was magnetite. Magnetite contains iron and responds strongly to a magnetic field. Its abundance, grain size, and magnetic properties can be measured even when the particles are microscopic. Different rock regions beneath Antarctica contain distinct magnetic signatures, allowing sediment to function like geological evidence carried away from a hidden crime scene. When an ice sheet is small, glaciers erode and transport material from a more limited area. As the ice advances farther across the continent, it reaches new bedrock and sends different mineral mixtures toward the ocean. The sediment core therefore records changes in the ice sheet indirectly. Scientists cannot watch a glacier that existed 4 million years ago, but they can examine the material that glacier scraped from the continent and deposited offshore. Between approximately 4.1 and 3.8 million years ago, the researchers found extremely low magnetite concentrations. They interpreted this interval as the smallest extent of the West Antarctic Ice Sheet in the Amundsen Sea sector during the entire record, which began around 4.33 million years ago. At that time, the planet was warmer than today. Atmospheric carbon dioxide and ocean temperatures were higher, and the West Antarctic Ice Sheet was highly dynamic. Previous drilling research also found that the Amundsen Sea region experienced major retreat during the warm, early Pliocene. Then the long cooling began. From about 4.1 million years ago, the sediment record indicates that the ice sheet started expanding in step with falling global temperatures. The advance was not a single uninterrupted surge. Glaciers fluctuated, coastlines changed, and ocean conditions continued to vary. But the long-term direction was clear. As the planet cooled, West Antarctica gained ice. The dramatic transition arrived around 3.2 million years ago. Fine-grained magnetite increased substantially in the sediment. The mineral evidence pointed toward a stronger and more persistent contribution from the Thwaites Glacier catchment. This suggests that ice advanced far enough to erode and transport more material from that region. The researchers argue that the timing may represent the crossing of a climatic threshold. Instead of responding proportionally to every small decrease in temperature, the ice sheet may have reached a point where several conditions began reinforcing one another. Imagine cooling a container of water. Its temperature falls gradually, but it does not become a slightly more solid liquid with every degree. Once it reaches the freezing point, its physical state changes. An ice sheet is far more complicated, but the principle of threshold behavior is similar. Gradual climate forcing can eventually push a system into a different configuration. Cooling air allows more snow to survive summer melting. A larger ice surface reflects more sunlight back into space. As the ice thickens, its upper surface rises into colder air. Expanding sea ice can alter the exchange of heat between the ocean and atmosphere. Colder ocean water reduces melting beneath floating ice shelves. Each effect can support additional ice growth. Changes in elevation may have been especially important. A thin ice sheet resting at low altitude experiences relatively warm air. Once snowfall and cooling allow it to thicken, the surface rises. Higher elevations are colder, which allows even more snow to survive. This creates a feedback in which growth makes further growth easier. The shape of the land may also produce thresholds. A glacier moving across a basin can remain sensitive while its grounding line sits over deep water. If cooling allows the ice to advance toward shallower terrain or more favorable pinning points, the new geometry may stabilize it. The study does not prove that one mechanism alone caused the shift at 3.2 million years. Instead, the sediment record shows that the ice sheet's behavior changed at approximately the same time that global climate crossed into a colder state. After this transformation, West Antarctica appears to have maintained a larger long-term extent. The elevated fine-grained magnetite indicates that sediment continued arriving from the Thwaites region over an extended period rather than during one isolated advance. The ice sheet did not become permanently fixed. Glacial and interglacial cycles continued, and West Antarctica repeatedly advanced and retreated. The study focuses on changes occurring across millions of years rather than resolving every individual ice age cycle. Another major shift occurred after roughly 900,000 years ago. The record shows that the long-term expansion of the West Antarctic ice sheet largely stopped. This coincided with atmospheric carbon dioxide and ocean temperatures becoming comparatively stable over the same broad timescale. This history matters because modern warming is now pushing the system in the opposite direction. The ancient record documents how cooling allowed the ice sheet to cross into a larger state. It does not provide a precise modern collapse temperature, and the researchers do not claim that today's ice will simply reverse the same path at the same threshold. Ice sheets can show hysteresis. That means the climate required to build a large ice sheet may differ from the climate required to preserve it. Once major retreat begins, returning temperatures to an earlier level may not immediately rebuild what was lost. A boulder resting in a shallow depression illustrates the idea. A strong push may be required to move it over the edge. Once it rolls downhill, merely removing the push does not return it to its original position. West Antarctica may behave in a similarly uneven way. Growth and collapse can follow different routes because ice thickness, bedrock geometry, ocean access, and grounding line position change as the system evolves. The new sediment record therefore acts as both a history and a warning. It shows that the West Antarctic ice sheet is strongly connected to global climate. It also shows that its response may not always be gradual. For hundreds of thousands of years, cooling and ice growth can appear progressive. Then a threshold is crossed, erosion patterns change, and the ice sheet moves toward a fundamentally different state. The discovery also places Thwaites Glacier inside a much longer story. Today, Thwaites is often discussed as a potential gateway for retreat into the interior of West Antarctica. Millions of years ago, the same catchment apparently became a major source of sediment when the ice sheet expanded after crossing a colder climate threshold. The glacier now associated with future ice loss also preserves evidence of ancient ice growth. Scientists recovered that evidence from grains of magnetite smaller than sand, carried away from buried Antarctic rock and deposited layer by layer in the deep ocean. Those particles reveal a continent responding to global cooling over millions of years. They show a smaller ice sheet beginning to grow around 4.1 million years ago, then undergoing a major transformation around 3.2 million years ago. The lesson is not that Antarctica always changes suddenly. It is that slow pressure can build until a vast system begins behaving differently. West Antarctica may look permanent from space, but its own sediment record tells another story. It has expanded, retreated, crossed thresholds, and reorganized itself as the climate changed. The mud beneath the Amundsen Sea has now preserved one of those transitions, revealing how a gradual planetary cooling helped transform West Antarctica into the massive ice sheet we recognize today.